Today I'm going to present joint research with my collaborators from China. In this work, we first identify performance bottlenecks of Linux AMD, the software RAID, when supporting very fast SSDs, and then propose a solution, which is a stripe-threaded architecture, try to remove and alleviate this bottleneck. So let me first give you a quick primer on RAID. I don't think I need that, but just for the purpose of other audience. So RAID, which stands for Redundant Array of Inexpensive Disks, was designed to provide high I/O throughput by striping data across multiple disks, and high reliability by leveraging data redundancy. In an n-disk RAID, data are organized in stripes of n chunks each, and the block addresses are algorithmically mapped to chunks on the disks. So depending on the whether or how data redundancy is used for reliability, RAID is organized into multiple levels. And that can be roughly divided into two categories: non-parity RAID, for example, RAID 0, which is stripe only, or RAID 1, which is mirror only, uses replicative redundancy, or they can be a parity RAID, which uses parity redundancy to provide data reliability that can tolerate one or more disk failures. So while read and write in non-parity RAIDs are straightforward, essentially you just write and read to the constituent disk as normal. However, for parity RAID, write operation, particularly partial stripe write, is more complicated, which involves reading the affected data chunks and the old parity chunks, and then apply the parity operation to generate new parity, and then write the new data and parity chunks back to the disk. So this is also called, partial write penalty. So the Linux software RAID module, referred to as multiple disks or MD, is the most commonly used software RAID evolving with the Linux kernel. So currently, MD supports various RAID levels and RAID compositions. So instead of using a hardware RAID card, MD uses the host CPU and memory resources to provide RAID functions. Therefore, MD is highly portable and compatible with many different storage devices, including HDD, SSD, and NVMe, and so on. So with the modern SSD continuously providing high write throughput, as indicated in the figure here, a single SSD is poised to provide more than 10 gigabytes per second write throughput. The question is, can the latest MD keep up with this pace? Or alternatively, can MD fully leverage the increasing high performance of the individual storage devices? So this question motivated us to revisit the SSD-based MD RAID. So we deploy 6 SSD devices to construct non-parity RAID 0 and parity-based RAID5 and RAID6. We also enabled the multi-worker mechanism of MD, which was introduced in 2014 to better utilize the performance of SSD devices and enables multiple functionally equivalent worker threads to process stripes concurrently. We enable up to 64 worker threads to maximize the MD performance. So as we measure the MD performance running on 3 types of SSD devices, and their I/O characteristics are listed in the table here. So as you can see, for the high-end SSD, the cumulative write throughput can reach up to 14 gigabytes per second. So the figures here report the throughput performance of the different RAIDs. So in all the cases, the write performance and scalability of the non-parity RAID 0 far exceed those of the parity-based RAID5 and RAID6. Especially parity-based RAIDs fail to scale for higher performance SSDs. The write throughput of RAID5, for example, and RAID5, RAID6 actually is only 1/7 of that of the RAID 0 on NVMe SSDs. So even the most stripe write friendly access pattern, which is the full stripe write, which doesn't involve the read, modify, and write, still there is a big gap, as you can see here. So to further analyze the performance contribution of the multi-worker mechanism in the parity-based RAID, we invoke up to 64 user threads and enable the multi-worker thread mechanism with the number of actual worker threads varying from 1 to 64. MD with 64 more worker threads has a write throughput improvement of less than 4 times over the single worker thread. And its performance gain peaks at 16 worker threads. So as a result, even with multiple worker threads, parity RAIDs still fall far short of fully leveraging the individual device performance. So to find the root cause of this write inefficiency of MD, here we analyze the architecture of parity-based MD. MD introduces an N-for-all processing model to handle stripe write tasks, where multiple worker threads, where N represents, process all stripes concurrently. So MD deploys a centralized stripe cache that temporarily stores the incoming block IOs, and these BIOS are aggregated at the granularity of stripes. And each stripe has its own stripe head containing metadata such as the stripe states and device states. And actually, for each stripe, there are over 50 states, so it's quite complicated. So MD module invokes multiple functionally equivalent worker threads to process stripes asynchronously and non-exclusively. And of course, with the exception of when accessing global shared data. So this was designed to utilize the CPU functionality sufficiently to absorb more requests for reducing actual IOs, so by accumulating or batching all those IOs to the same stripes, which is efficient when using HDDs or SATA-based SSDs. However, it is upper bounded in its processing scalability that fails to keep up with the fast devices. So next, we will analyze the multi-worker concurrency control of MD. So MD uses a spin lock called device lock to control concurrent accesses from worker threads and user threads to all the stripe lists and metadata. So in the case when multiple worker threads exclusively access the stripe list, the spin lock will cause severe contention among these threads. So the spin lock actively spends CPU cycles, obviously, to compete for locks, consuming significant CPU resources when competition occurs. So in fact, the stripe list is a hotspot due to the worker thread's non-exclusive stripe processing. So the stripe write process workflow roughly consists of 5 consecutive stages, from inserting the block IOs into the stripe head to handling the stripe write itself, which has 3 stages, as mentioned earlier: read, modify, and write. And finally, clearing the stripe head. So different process stages may be handled by different worker threads in this setting. Now, to complicate things further, the worker thread handles each stripe write stage, so there are 5 of them, with 4 steps. Here we take the read stage as an example to illustrate the overhead. So first, the worker thread has to acquire the device lock for fetching a stripe head from the handle list, which causes lock contention among the worker threads. And then the worker thread will analyze the large number of states of the corresponding stripe to determine the exact handling operation following this. However, most of the stripe states are shared among user threads, worker threads, and even some other IO threads. So as a result, AMD has to use semaphore and RCU read lock to protect state analysis transactions. So that's increasing CPU overhead further. So therefore, we suspect it is this area, this protected access to share lock and also the share states that would be the culprit for this inefficiency. So after the stage is handled, worker thread will release the SH and insert it back to the stripe list, again invoking the lock. So again, causing contention. So these 4 steps, as I mentioned, actually is associated with every one of the 5 stages. So as a result, clearly this is going to have a very significant impact on the performance. So to verify our suspicion, we investigate the CPU usage distribution when running MD with varying number of worker threads. And we use the perf tool to measure the CPU cycles of key functions with worker threads, with a worker thread. So the results show that the CPU becomes a notable bottleneck on concurrence control in MD. So on the one hand, the global device lock consumes a dominant 55% of CPU cycles in the 64 worker thread case. On the other hand, CPU cycles responsible for disk I/O and the parity calculation decrease as the number of worker threads increases, accounting for less than 10% at 60 worker threads. So in conclusion, while AMD provides more CPU resources by enabling the multi-worker mechanism, fewer CPU cycles are used to drive IOs. Therefore, fast device, storage device are not fully utilized, as we suspected. So to solve this write inefficiency of parity-based RAID, we propose a stripe-threaded architecture, StRAID for short. So the goal of StRAID is to reduce CPU overhead by optimizing the concurrent stripe handling process and minimize the partial stripe write penalty. So there are dual goals. To achieve the first goal, StRAID assigns a dedicated worker thread to exclusively handle the corresponding stripe. Multiple worker threads process their own stripes independently, therefore exploiting the intrinsic data parallelism among the stripes. Compared to MD, StRAID removes the centralized stripe head lists and their corresponding concurrent operations, thus reducing the lock contention among multiple threads. Furthermore, StRAID minimizes the number of shared stripe-related states and global states checking among worker threads. Because of a dedicated worker thread handles stripe exclusively. So the concurrent stripe handling process and now, we just described the first goal. However, how to achieve the second goal is not trivial. So there's also an issue of how StRAID coordinate multiple worker threads. So to effectively coordinate multiple worker threads, StRAID proposes a stripe state table that maintains a set of required shared stripe states and per stripe locks. SST is a globally shared data structure among worker threads where each entry is uniquely associated with a physical stripe. To provide lockless access features, each entry in SST can only be exclusively modified by its dedicated worker thread using atomic operation at any time. So in StRAID, a write triggers a dedicated worker thread to immediately and exclusively handle the corresponding stripe write, which does not address the costly partial write penalty, our second goal. So to optimize the partial writes, StRAID presents a two-phase stripe submission mechanism. So it optimistically aggregates writes belonging to the same stripe by enabling a batching queue in each worker thread. The Linux MD aggregates partial stripe writes to full stripe writes by actively or passively postponing stripe handling tasks. Different from MD, the two-phase submission aggregates writes within a limited time provided by the stripe access itself. So we should use an example to describe the StRAID's concurrence control method, where 4 I/O threads issue block requests to StRAID concurrently, where BIO0 targets the stripe S5, and BIO1 through BIO3 target the same stripe S8. At the beginning of the timeline, worker thread 0 and worker thread 1 receive BIOS from their corresponding user thread and acquire their stripe locks to begin stripe processing independently. The BIO0 and BIO1 can be handled independently, as I mentioned, because they target different stripes. And these two worker threads first initialize the stripe table in SST, then it determines the reconstruction method for this stripe and reads the required parity data and parity chunk and data chunks from the disk. So StRAID utilizes the latency of waiting for read data to opportunistically aggregate requests. So during this period, while you're waiting for read data for the data chunks and parity chunks, if there are requests coming in addressing the same stripe, then you batch them. It's very simple. And by setting the is batching flag in the corresponding SSD entry. So shortly after worker thread 1's arrival, a second worker thread 2 arrives and seeks SSD, only to find that the targeted stripe is locked but enabling batching. So worker thread 2 inserts its BIOS to the batching queue of the handling thread, worker thread 1, and then suspends itself. When a worker thread completes its batching phase, it immediately transitions the stripe into the frozen phase by using an atomic cast operation to update SSD. After that, the stripe is not allowed to aggregate any further requests. So the newly arrived BIOS from worker thread 3 are consequently blocked and must wait for the stripe A to be finished or released, the stripe head released. Then the dedicated WT1 coalesces all the requests it has accumulated in its batching queue and processing them as a whole, which means re-executes parity read in accordance with the aggregated request and performs parity calculation and data parity writes back to the disk after reconstruction. So finally, the dedicated worker thread 1 clears up the stripe states of SA in SSD and releases the stripe back, the stripe lock. The corresponding waiting thread WT2 will also return successfully. So in the next phase, the worker thread 3 should reacquire the stripe lock to become a dedicated thread for handling its requests. So this is how the ST thread works in a nutshell. So to find out how it does in dealing with traces, we run extensive experiments on the server and 3 types of storage devices with their details described in the table. So essentially, the latest SSD or the high-end SSD, and also the persistent memory, Optem, trying to say how much ST-RAID can go with faster device. We also use a RAM disk to emulate even faster SSD and see how it does. And we use both micro benchmarks and select 3 representative block traces from Microsoft, Ali, Pangu, and FileBench as trace-driven micro benchmarks to evaluate ST-RAID. So here are the results, micro benchmark results. The figure reports the write throughput of ST-RAID and MD with partial stripe write and full stripe write. So ST-RAID achieves up to 2.5 times higher write throughput than MD with a single thread. It indicates that ST-RAID can effectively reduce the overhead of handling stripe states, thus scales better than MD with highly concurrent and intensive workloads. The right figure indicates the average request latency of ST-RAID and MD, which also shows the advantage of ST-RAID over MD, notably. Moreover, ST-RAID does not affect read performance, and the average read throughput difference between MD and ST-RAID is less than 5%. So the left figure reports. So compared with CPU utilization of ST-RAID and MD with 64 threads, the left figure shows that ST-RAID reduces up to 90% lock overhead and almost all the stripe state checking due to the stripe threaded architecture. Features in ST-RAID such as the two-phase stripe submission mechanism incur less than 5% of CPU consumption. The total CPU utilization of MD is up to 6.3 times higher than ST-RAID with 64 user threads. However, the ST-RAID gains higher throughput and efficiently uses twice as much CPU resources for computing exclusive OR and issuing IOs. So it spends most CPU cycles on IOs and the real work. For example, MD with 4,495% CPU core utilization consumes only 2.1 gigabyte per second of the SSD bandwidth, in contrast to ST-RAID that consumes 6 gigabyte per second of the SSD bandwidth with only 704% CPU core utilization. So to get a sense of how far can ST-RAID go with even faster SSD in the future, we test sort of the upper bound using RAM disk and PM. So the throughput of ST-RAID on PMs is up to 50% and 35% higher than MD on partial stripe and full stripe writes. We find that ST-RAID on PMs shows up to 25% higher throughput in partial stripe write than that on SSDs. This is because PM has 1 order of magnitude lower read latency than SSDs. Thus, ST-RAID could handle stripes more efficiently. At 64 user threads, ST-RAID on DRAM, RAM disks reaches more than 35 gigabyte per second write throughput, in contrast to their MD counterpart of less than 6 gigabyte per second. So it shows that ST-RAID has the potential to effectively exploit faster storage devices like the emerging PCIe 5.0 SSDs in the near future that is poised to reach more than 10 gigabyte per second per device. So here is a micro benchmark results. So the average throughput is 2 times to 2.8 times higher than MD. The mean average and 99 percentile latency is 10.3 times and 49% and 25% lower than MD. And to conclude, we presented a stripe threaded architecture for MD so that it can better support high-speed storage devices. And the result indicates its design is effective in achieving its design goals. Thank you.